This is an introduction to electron configuration. This information will be helpful when you learn how to do actual electron configurations in another lesson. Now, you may remember that Schrodinger's electron cloud model of the atom tells us that electrons do not travel around the nucleus in a fixed orbit. Rather, they move around in such a way that they create what we call an electron cloud. Electron configurations are designed to show us how an atom's electrons are actually distributed. They do this by providing the energy level arrangement of the atom's electrons and the pattern of movement of those electrons. To do this, electrons are actually arranged into what we call energy levels. And there are 7 energy levels. Each one of those energy levels is then divided up into sublevels, which we call orbitals. Now, there are different types of orbitals, each one having a different shape, which we will discuss in a minute. There are s orbitals, there are p orbitals, there are d orbitals, and there are f orbitals. Orbitals are basically regions where we are likely to find an electron at a given point in time. To equate this to the periodic table, you'll notice, and we're going to move helium over to here for this purpose, that these orbitals are located in specific areas on the periodic table. Your alkali metals and your alkaline earth metals are where you will find your s orbitals, whereas you will find your p orbitals over here in this region, which are your metalloids and your nonmetals. Transition metals represent all your d block or your d orbitals are found there. And down here where the lanthanides and actinides are, you'll find your f orbitals. Now, it's important to note that our primary energy levels kind of work like this. For the s's, they're 1, 2, 3, 4, 5, 6, 7. So you would have 1s, 2s, 3s, 4s, 5s, 6s, 7s. The p's start in the 2's, 2, 3, 4, 5, 6. So these would be 2p, 3p, 4p, 5p, 6p, and actually you do have you have the potential of a 7p there. Your d blocks will start with the 3, so you have 3d, 4d, 5d, 6d, and your f's start with 4, 4f and 5f. Okay. Now, looking at this periodic table, you'll notice that for s orbitals, sorry about that, couldn't get this to draw, s orbitals, there are actually 2 electrons, but there's only 1 orbital in each energy level. Because actually you'll learn a little bit later that each orbital holds 2 electrons. In the p's, there's 2, 4, 6 electrons, or 3 orbitals. For d's, if you look at it this way, you will see there's 2, 4, 6, 8, 10 electrons. For d's, there are 10 electrons, representing 5 orbitals. And when you get down to your f's, 2, 4, 6, 8, 10, 12, 14. For for F's, and I got to write this up here because I didn't leave enough room, there are 14 electrons or 7 possible orbitals in a given energy level. So S's, there's 1 orbital in an energy level. P's, there are 3 p orbitals in a given energy level. There are 5 d orbitals in a given energy level, or I should say, and there are 7 F's in a given energy level. Now, each orbital has a specific shape to it. S orbitals are spherical, so what you will see is that the electrons can be located anywhere in that sphere. You get an hourglass type shape for your p orbitals, clovers for your d orbitals, and I'm not exactly sure what shape you would call this, for your f orbitals. Keep in mind that all orbitals have a 3-dimensional shape to them, even though they're drawn 2-dimensional here. Electrons can move anywhere within the shape of that particular orbital, so they can be in any place at any given time within that sphere, or that hourglass, or that clover, etc. Orbitals do become larger as you move down the periodic table. Now, in order to understand electron configurations, there are a few principles that you need to know. The first one is the Aufbau Principle. In it, it states that an electron will always occupy the lowest available energy level first. What that basically is saying here is that it's going to occupy one s orbital before it can occupy any other orbital, that first electron and that second electron. 2 s's will be filled next, then your 2 p's, then your 3 s's. Notice as the 1's get filled first, then your 2's, then your 3s, then your 3p, 4s, 3d. Notice right here that one energy level is a little further out than the other, but they must fill in this order. Also, all orbitals in a given sublevel have the same amount of energy. That means, if we're talking about the orbitals in 4f, for instance, every one of these orbitals have exactly the same amount of energy. None of them has more energy than the other. The same would actually go if we looked at 7 s's. Well, that's not a good example. Let's do the 4d's. Every one in this particular one would also have the same amount of energy. The energy levels between these two are not equal. But within here, they're equal. And within here, they're equal. Pauli's exclusion principle tells us that a maximum of 2 electrons can occupy an orbital. So, for instance, in an s orbital, of which there's only 1 in a given level, I can only have 2 electrons. Each one of those equal an electron. In p's, which we've already discussed earlier, there are 3 orbitals to a specific p level, sublevel. Again, I can only have 2 in each one of these orbitals. Same thing would happen for d's and for f's. D's having 5 boxes or 5 orbitals in a given level, and again, only 2 of them, electrons, go into each orbital, and F's would have 7. It's also important to note in Pauli's exclusion principle that electrons in the same orbital spin in opposite directions. So if I have 2 electrons, one of them is going to be spinning in this direction, and one in the opposite direction, which is the reason why we draw the boxes like this. Each one of these represents the different spins. Notice the arrows go in different directions. The last rule you need to know is something called Hund's rule. It basically states that electrons will spread across a sublevel before pairing up. So in other words, if I was sitting here in the 2p's, okay, my electrons, if I had 4 electrons, I would place them like this. The first one would go there, the second one would go there, the third one would go there, so I have one in each one of the p orbitals in that level before I put in the next one. Okay, same thing would go into, example would go if I went into 3p, which is right here, and if I had 3p3, I would be placing my electrons like this. I would not place them, my 3 electrons, like this, because I have to put something in each one of these first, each one of these orbitals first, before I can go ahead and put a second one in anywhere. So that would be wrong. This should give you enough background so that you can go on to the next lesson and learn how to actually do electron configurations.